Now we can use these double angle formulae for a few different things. Sometimes they're really handy to prove an identity, and they're also quite handy for finding exact values. Now you've got to sometimes use a little bit of problem solving to work out how to use them to find your exact values. So here's a good example. Let's find the exact value of the tan of 22.5 degrees. Now, as soon as I see that 22.5, I'm thinking, hey, 2 of those is 45. Perhaps I can use that somehow. Now, tan of 45 also jumps into my head as being 1 because it's an exact value that I already know. So thinking through those things at the start to work out what you need to do, knowing that you need to double this and somehow use it here, it makes sense to me that I'm going to need to say the tan of 45 degrees. Now, if 45 is what I have here, and that's 2 lots of theta, then clearly theta is going to be 22.5 degrees, and that's how I'm going to use this. Now, it might seem a little unnatural in that what I've got on the left-hand side is something I already know, and what I'm going to have in a couple of different places on the right-hand side is something I don't know, but I should then be able to tidy up and solve for the unknown. So let's have a look at how we'd do it. We'd say this is 2 multiplied by the tan of 22.5 degrees, and on the bottom we need 1 minus the tan of 22.5 degrees, 22.5 degrees, squared. Now you can write tan squared 22.5 like that, or you can write it like this, squared. Doesn't matter which way you do it as long as you understand what it is you've done and you know how to read both forms and understand what they mean. I'm going to write it like this for now, just so I keep it really straight in my head what's happening. All right, now I know that this side equals 1, so I could replace that whole thing there with a 1. And solving this, first thing I want to do is get rid of the denominator, so I'll do that by multiplying both sides by it. So if I've got 1 over here and I multiply by the denominator, clearly that whole denominator is going to end up over this side here. So I've got 1 minus the tan of 22.5 degrees squared is equal to 2 times the tan of 22.5 degrees. Now, this is quite tricky. It's actually a quadratic, and it doesn't jump out as one straight away, but I've got something squared, I've got some of those things not squared, and I've got some numbers. So let me just make this simpler for you. If I had something like 1 minus x squared is equal to 2x, it would be much easier to spot there that I've got a quadratic. Now, how do I solve something like that? I have to get everything on the same side, make it equal 0, and then factorize it, or I could complete the square, or I could use the formula. If I'm completing a square, perhaps I only need to get the x's on one side and have the numbers on the other, but to my way of thinking before I tackle any of those 3 methods, I like to just get everything on one side and let the whole thing equal 0. So to me it makes sense to get everything on the side that's got positive x squareds in it. So if I put this over here and add x squared to both sides, and I've got my 2x there, and I subtract 1, I have this. Now I can quickly and easily see that I can't factorize it, because if I have x minus 1, I'm going to not get my plus 2x. So I need to either complete the square or use the formula. Take your pick. Let's use the formula this time and say, x would be equal to negative b, that's minus 2, plus or minus the square root of b squared, or 2 squared is 4, minus 4 times 1 times the negative 1. So in other words, that's plus 4, because I'm subtracting negative 4, aren't I? All over 2 times 1, which is 2. So I've got negative 2 plus or minus the square root of 8. Now the square root of 8, think that through, that's the square root of 4, 2, times the square root of 2. So what I've actually got here is negative 2 plus or minus 2 root 2 all over 2. Now I can simplify that further, can't I? I can divide both these terms on the top by 2, and basically I can get here that x is negative 1 plus or minus root 2. Now I've got 2 choices here, and this whole time, can you see that what substitution I've made here is that x is equal to tan 22.5 degrees. So I need to make sure I remember that, okay, because x isn't equal to anything. There wasn't an x even in my question. Basically, I've just used x being equal to that to tidy up my thinking, to spot that it's a quadratic and to solve it quite happily. So all the way down here, instead of having an x here and here and here and here, I could have written tan of 22.5 degrees. And in fact, you can keep that in there. You don't need to put the x's in. But I've put the x's in to explain what I'm doing, because I think you can see that once the x's are in there, it's much easier to understand why I've solved it this way. So I guess between here and here, you'd go off here and you'd put this over on the side, or you'd actually put it in here. You'd say let x equal all of that. Okay, so x is equal to this, but what is tan 22.5 degrees? Could it possibly have two values? Why would it have two values? Think through what the tan curve looks like. It's something like this. And when x is 22.5 degrees, we know that we're going to get a positive answer. We're not going to get a negative answer. Now, sometimes this happens. When you solve something, because it's a quadratic, it will give you two potential solutions. That doesn't mean that both of them are correct. You need to look at your situation, and often you need to reject one of the possibilities. So here we basically have root 2 minus 1 or negative root 2 minus 1, which is going to be a negative answer, and we need a positive answer. So therefore I'd say that tan of 22.5 degrees is equal to root 2 minus 1, because we know that tan of 22.5 degrees is greater than 0. And I just write that like that. It's positive, so it's greater than 0. And so there we've solved it. We've got an exact value. It's root 2 minus 1. And it was a bit of a process to go through, but the more of these that we do, the easier they'll get. You can also use these formulae to rearrange expressions or to prove identities. So in this example, we need to express cot 2x in terms of cot x. Now, we don't have a formula for cot anything, so we need to start by saying that cot 2x is equal to 1 over the tan of 2x. Now we can say we've got 1 over this formula here, where we've just replaced all the thetas with x. So we can go ahead and say, well, that's 1 divided by, and I'm just treating this as a divide by, and I'm putting in all of this, 2 tan x over 1 minus tan squared x. And then dividing by a fraction, obviously I can multiply it by the reciprocal. So I get here 1 minus tan squared x on the top, and I get my 2 tan x's on the bottom. Now, a couple of ways you could go from here. It's really tempting when you see tans and you want to get cots to just say, hey, I know cot x is equal to 1 over tan x, and vice versa, tan x is equal to 1 over cot x. Can I just change the tans into cots and flip this whole fraction upside down? Well, no, I can't do that, and you need to be really careful that you don't, because this fraction's got 3 individual terms in it, and you need to treat each of them separately. So one way you could go is you could say, look, I've got 3 terms here. How am I going to get them in terms of cot? I know that if I do 1 over tan, then this one will turn into a cot. But doing tan squared x over tan x, that's still going to give me a tan x, isn't it? So really, to make this one not have any tan x in it anymore, I need to divide it by tan squared x. And in fact, that would work for this one as well, because 1 over tan squared x will be cot squared x. And in fact, dividing tan x by tan squared x will give me something over tan x. So that will turn it into cot as well. So thinking through what I'm doing here, if I divide all terms by the tan squared x, what I'm going to get is, and I can do the working here just so I don't leave anybody behind, this line of working would be entirely optional, and I'm doing it here, but I'd be fine with you doing this in your head if you're happy to do it. I'm dividing all 3 terms by tan squared x. So now I can see what's happening. 1 over tan squared x is cot squared x. Tan squared x over itself is 1. And on the bottom, I can cancel a tan x with one of those, and I've got 2 over tan x, which is just 2 cot x, and I'm finished. All right, so that's one way you could go, dividing all of the terms by something and figuring out what you'd need to divide it by to get what you want. Another way you could go is just to make the replacements as you go. So if I say here, look, 1 is always 1, and so from here this would be another way to go. I've got 1 minus tan squared x, that's 1 over cot squared x, isn't it? And 2 tan x, that's 2 over cot x. Okay, so now I've just made these replacements in each of the individual parts. Now I just need to tidy it up. So on the top here, we could make these 2 things have a common denominator by saying we've got cot squared x minus 1 all over cot squared x. So here I just said this is cot squared x over cot squared x, and I brought these 2 together. And then I'd divide by, because this big line here means divide by, and I could do that this way, and divide by 2 over cot x. But even thinking that through, again, I can save myself a bit of time by saying, hey, if I'm dividing by a fraction, I'm going to want to multiply by the reciprocal. So I could probably just multiply straight off by the reciprocal of what's on the bottom there, just to save myself a little bit of time. And now, same as what happened over here, I can see that my cot x is going to cancel with one of those, and I'm going to get the exact same answer as this. On the top, I've got the cot squared x minus 1, and on the bottom, I've got 2 cot x. So, slightly different strategy. This one might appeal to you more because we never really had to make a big decision about what to do. We just changed each term from tan to cot and then sorted it out. This one, we spotted something we could do, and then we did it. This line here is completely optional. You might do that in your head and go straight from this line to this line. Similarly, this line here, you could do in your head and leave this out. I wouldn't recommend leaving it out at first. Wait till you've done a bunch of these and lines like this are getting really boring and you're like, oh, I can see what to do here. And if you're getting them right, feel free to leave those lines out. But if you're getting them wrong, go back to writing them in, because it's better to take that extra bit of time and get it right than to take a shortcut and have your work filled with mistakes. And we can also use these formulae to simplify expressions. So this one's got some inverse trig in there combined with some normal trig. So to do this, we're noticing that we've got the sign of 2 lots of something. And so that really triggers me into thinking that this formula might be helpful. Now I know how to find the sign of 2 lots of theta. So effectively that's my starting point, is to say, let's let theta equal this part here, the inverse cos of 4/5. Now we know how to rearrange that. That means that the cos of theta is 4/5. Now let's think what that really means. That means we've got some right angled triangle where if we labelled theta, then the opposite side over the hypotenuse would be 4/5. And in fact, this looks like a 3-4-5 triangle, and even if it wasn't, we could use Pythagoras to figure out what that missing side in the right angled triangle would be. Now, why do we want to do that? Well, effectively what we have here is sine of 2 theta. So if we rewrite what we had then, we can say that sine of 2 inverse cos 4/5 is equal to sine 2 theta. Now sine 2 theta is 2 times sine theta times cos theta. So we can write this down now. It's 2 sine theta cos theta, where we already know theta equals inverse cos of 4/5. Okay, now we've already got ourselves an expression for cos theta here, and that's handy because we're going to need it. But we need to find sine theta, and now that we've got our little drawing of our right angled triangle, we can see that sine theta is just 3/5. So then our answer to this is really spelled out nice and simply here. We've got 2 times the sine of theta times the cos of theta. Now one of those came out simply just by defining what theta was. We could easily see what cos of theta was. And by drawing our right angled triangle, we could get the other one. And now we've just got some simple arithmetic to do here, and we can see that on the top here we've got 24, and on the bottom, 24, and on the bottom we've got 25. So we end up with 24/25, and the answer is really quite nice and simple.